Well, good morning, everyone. I am so delighted to see you all here today, and I'm pretty excited about what we have on offer for you today. So my name is Renee Barlow. I'm the VP of Entrepreneurship and Innovation for Economic Development Lethbridge. First, in land acknowledgement before we begin, I want to acknowledge that we're gathered on the traditional territories of the Siksika Tisabi, the Blackfoot Confederacy, which includes the Siksika, Kainai, and Piikani nations. This land is also home to the Métis Nation of Alberta Region 3 and has long been a place of gathering, learning, and innovation. We honor the First Peoples as the original innovators and knowledge keepers of these lands, whose deep understanding of complex systems, natural cycles, and interconnections have shaped life here long before any of us arrived. As we explore one of today's most advanced technologies, quantum computing, we do so with the respect and for the wisdom and ingenuity that has existed here for generations. I'm truly honored to welcome you, many of you coming from all different parts of the world online, for the very first SuperQ Quantum Masterclass, right here at the first Quantum Super Hub, based at Tech Connect in Lethbridge, Alberta. You are not just participants today, you are the inaugural cohort stepping into a new chapter of quantum-powered innovation. This hub is the first of its kind in the world. And it's not just a lab or a research facility, it's a business accessible, community-driven gateway to the future of computing. Together with our partners at Quantum, we've built a place where real businesses, researchers, and innovators can start using the world's most advanced computing tools, not years from now, but right now. This masterclass is part of a larger movement, one that brings quantum out of the lab and into the boardroom, farms, factories, classrooms, and startups. As the technology moves from a science project to a commercial reality, it's essential that industry leaders understand not just the what, but the why now. This isn't theoretical anymore. As we speak, quantum computing is being used to optimize agri-food operations, model supply chain disruptions in global trade, accelerate drug discovery, and enhance cybersecurity for the post-quantum era. And today, we'll get to see what that actually looks like. Before we begin, I want to thank the team at SuperQ for being a partner with Economic Development Lethbridge. And I'd like to thank all of you for joining us at the beginning of something bold. By being here, you're helping to shape the future, not just for your business or organization, but for our region, for our country, and our world in the industries we care about most. It's my pleasure to introduce the visionary behind this platform, Dr. Mohammed Khan, CEO of SuperQ Quantum. He brings nearly 2 decades of deep tech experience from Silicon Valley to Cambridge, and he's leading the charge in making quantum technology practical, usable, and results-driven. Dr. Khan will walk us through today's masterclass and share a live demonstration of how SuperQ works in action. So let's begin.
Okay, so thank you so much, everyone, for being here. And Renee, thank you so much for organizing this. And yeah, boy, I didn't expect such a crowd. You know, we have such a large cohort here in attendance, in present, in person, as well as online. So really appreciate this. And this is further a testament that Tech Connect is a thriving community of innovators, entrepreneurs, and curious minds who just want to leverage deep tech and get their hands on it. So great. Okay, so let's get rolling. We have a full agenda actually. So we'll talk about what the platform is. What is Super Platform? Okay, we'll talk about what is Super Hub and what can you achieve right here at Tech Connect. And then also, what's the vision? Where are we heading towards? And then how does the platform work? The internal mechanics of it. You'll see it in action. You'll see some examples of how you can use it today and what sort of problems you can use it for. Okay, so we have tried to keep it as less technical as possible. So it's going to be accessible. There's going to be technical information in there, but there's going to be a lot of business cases and examples. So hopefully that'll help. The whole point is to lower the technical and financial barrier to access quantum computing and supercomputing. Okay, so with that, let's dive in. Renee has already done a great job introducing me, but a little bit more background for those who don't know me. I was an academic, a researcher, professor for many years. Graduated from Cambridge. I was a professor at many different universities around the world, including University of Calgary, University of Lethbridge as well. And then I left academia and embarked on an entrepreneurial journey, which started at Tech Connect. So my first startup was based in Tech Connect. So this place is near and dear to me. And Renee has been a supporter and a collaborator and a partner ever since. So after that, yeah, a bit of a journey. Did stuff in San Francisco, in Dubai, in Calgary, built several companies, led them to different outcomes. And now working in the public markets as well, startup world to more scale up and public companies. So the company that we're talking about today and the platform we're talking about today is Super. It's part of SuperQ Quantum, and SuperQ Quantum is publicly traded on Canadian Securities Exchange. It is also traded in Frankfurt and the US. So a bit of a change from the startup world to the public markets. So yeah, there's a broad swath of experience here. So the purpose, though, behind my entrepreneurial endeavors is to bridge the gap between cutting edge innovation and industry implementation. Because having lived in both worlds, I noticed a big gulf between them. You know, it takes decades, years to get new advances in science implemented in industry, and we want to shorten that time span and reduce the overhead for doing that. Okay, so this is probably going to be the only slide where I'll talk a little bit technically, and I tried to make it as less technical as possible. What is quantum computing? So we'll start with a quick intro, and then we'll jump into the practical side of things. So if you look at our everyday computing, you know, imagine you're trying to solve a maze. Okay, and this is similar to you trying to optimize a business problem. You're trying to find the best pathway for you in your business problem. Okay, what is the best solution? In a classical approach, in a traditional computing approach, you would take one path. If you encounter an obstacle, you will backtrack. You know, you'll take another path. You encounter another obstacle, you backtrack, and you keep doing that until you resolve, until you reach your goal, you reach your outcome. The acceleration that quantum computing brings to this is that it is able to navigate all the different pathways at the same time. So that's the acceleration of quantum computing. It is not just a way of doing things fast. It's a way of doing multiple things at the same time in a concurrent manner. Now GPUs can do that to some extent as well. In GPUs, you have multiple cores, and each core can run a path. So in a way, you're stacking multiple computers, multiple CPUs to be able to do that. But there are limitations. You know, whereas in a quantum computer, you can do that with very small amount of computational resources. You don't need extensive hardware to be able to do that. So that's the speed part of quantum computing. And because of that, quantum computing is really good at solving problems where there is a large number of decisions and you want to find the best decision. Okay, so with that, we move on to Super, the practical side of things. So we started working in the high performance computing and quantum computing space about 3 years ago. 3 years ago, we started bringing quantum technologies into our industrial solutions. And we ran into some issues. Okay, the key issues were that our professional services team took significant amount of time to understand the problem, to work with the client, figure out what their needs were, you know, model the problem, get the data, ingest the data, come up with a solution, and then iterate over the solution. And the process used to take anywhere from 4 to 8 months. And then the cost to the client would be significant. It would become a 6-figure project or even more, in some cases, 7-figure projects. And we were not alone in this struggle. Other quantum computing companies like D-Wave, IBM, exactly the same situation, even worse, because their cost is higher, and then also their processes are a bit slower compared to what we were doing. So the question was, how do we scale? How are we able to create value for more businesses, and how can we lower the barrier, the financial barrier as well as the technical barrier? So about a year and a half ago, we started productizing our process. So whatever we were doing with our scientists, with our professional services team, we said, okay, let's build a platform that can automate that, or as much of it as possible. And that's how Super was born. Okay, so we named it Super because it's not just a quantum computing platform, it's a supercomputing platform, which basically means that it combines the best of classical high performance computing with different architectures of quantum computing, and it tries to find the best approach to solve a problem. So it's not limited to quantum, it's not limited to a particular hardware, it's not limited to a particular vendor. It tries to find the best solution among everything that's available. That's the idea. And it does so automatically, and it does so without technical overhead from the user. Okay, so started building it about a year and a half ago. Initially, our intention was that this is going to be a B2B platform, business to business. First we put it in the hands of our professional services. We gave it to some partner companies, their professional services, and then the intention was to roll it out to businesses. Okay, but as I spoke more about it, and as we started talking about it at Leap conference, in Ventures, at Web Summit, at all over the globe, people were so interested, and there was such an overwhelming response that we decided, okay, we have to create a retail user tier. We cannot just keep it in the hands of businesses. We have to make it available to everyday users, to people. That was a challenge because quantum computing is not that cheap, right? I mean, it's expensive technology. So we rolled our sleeves, we worked on it, and we also introduced a Trailblazer tier for retail users. And then we said, okay, now we can call it the ChatGPT of quantum computing, because we are putting it in the hands of people. So this is truly like a ChatGPT equivalent for quantum computing. So AI was there long before ChatGPT, and it was useful. It was being used by businesses, by larger corporations, but it didn't become mainstream until it was put in the hands of people. Right? And then people, what they did with it was they changed the direction of it completely. So it's not OpenAI that's dictating or Anthropic that's dictating the direction of how AI is developed. It's the people, it's the users. And we wanted to do exactly that with this technology. So we said, okay, we'll put it in the hands of people, and we'll call it the ChatGPT equivalent of quantum and supercomputing. And the reason is it is chat-based. In natural language, you can define your problems. You can start typing away. You can upload a PDF, a presentation, or a paper, a case study, anything, and start working on it. And you'll see it in action, how it helps you, go from problem statement to a fully productized solution. We'll see that. But yeah, that's the platform. We have our COO from joining us from Dubai, Krishna Ganesh, who's going to be doing a demo as well. So you'll see it. So still, it begs the question: why quantum and why now? Why today? Should we have done it maybe 2 years later? Or maybe we missed the boat and should have done it 2 years earlier? Not really. This is the perfect time. Okay, and there's a reason for that, and there's a plethora of reasons for that. One of which is the interest and investment levels in quantum computing. Countries, investors, VCs, everyone realizes that this is the time to get into this technology, and whoever misses it now is going to miss it. Okay, so the amount of investment in this technology has gone through the roof, even though last couple of years have been on the down low when it comes to startup funding, when it comes to even technology funding. But AI obviously has received massive attention. And then after that, quantum computing has received even more attention because it's the next thing, and people don't want to miss out on it. Particularly the funding in the public markets has gone up significantly. So you see in the chart, the private money has gone maybe a little bit down or plateaued a bit. But on the public market side, there is a lot of interest and significant investment. I mean, one of the reasons why we are public as well. There are other reasons, but that is one of the reasons as well. Second piece is the market projections. Where will this technology, the market size of this will be in 2 years, 3 years, 5 years? And the projections are projections. Like, for example, the AI projections you see here, 826. I mean, there is a projection that says it's 1,826 by 2030. So there is a delta. Like, AI is growing at a speed that maybe this is a very conservative estimate. But the same is true for high performance computing and quantum computing. There is a delta, and even these numbers that you see here can be a gross underestimate to where these technologies can be in 5 years. Okay, so this is the time to do core developments in the area. Okay. And then there have been scientific advances. There has been a series of scientific advances that have aligned perfectly. So since October, November last year, there has been some major announcements and major developments in the world of quantum computing and the world of supercomputing as well. Like, NVIDIA has come up with these amazing chips, traditional chips, conventional chips that pack a tremendous amount of computational power. And then on the quantum side, we have Google coming out with Willow. Okay, Microsoft coming out with Majorana. So Majorana is not a chip. Majorana is a topology, which basically means that it's a way in which you can potentially have millions of qubits on one chip. Doesn't mean we have millions of qubits right now, but once we do, we will be able to make them work together. So it's the connection part, the topology part that Microsoft has built. And then D-Wave, which is actually a partner company of ours, they came out with their quantum supremacy paper, which basically means that they have shown that there are computations that you can do on their computers, which you cannot do on classical machines, even in hundreds of years or thousands of years or tens of thousands of years. Okay, that paper was written jointly with the Quantum Matter Institute at University of British Columbia. So it's independent, there's independent scholarly verification there as well. And then comes Super, which is basically a gateway to access these and all other advances in quantum computing. How can you commercialize them today? How can you make use of them? So great science, fabulous, but how can we commercialize it? That's Super. That's the pathway. So May 30th, because that's when we started onboarding our first set of users. So we had a wait list, a long one actually, and we started onboarding first set of waitlist users on May 30th. And we're still kind of running through that waitlist. And we hope to be caught up completely by mid-August. So end of August, this is going to open up. Anybody will be able to sign up and use commercially. And then we'll talk about what access you will have at the hub versus what access you will have through the web. So yeah, that's why quantum. It aligned perfectly. And even since then, there have been made more and more advances coming out in the field that have made people realize that this is the time. And in the next couple of years, this technology will leapfrog even more. What can we do with quantum computing today? Near-term applications or today applications. What is possible today? And what is possible through Super particularly? So now I'm going to narrow it down a bit. I'm going to focus on stuff that you can achieve with Super now, or you will be able to do it in very shortly. So the biggest use case where Super excels is optimization. That's the first bullet point there, modeling large decision spaces. Okay. The word optimization we all use in our life, in different ways. But what does optimization really mean? It just means finding the best answer, which will increase your productivity or decrease your cost, in simple terms. There is a whole theory of it. There is a whole science behind it, all of that. But ultimately, you want to maximize profits, minimize costs in operations, in production, everywhere. That's optimization. And the good thing is that the technology we have access to today is really good at solving these kind of problems, or a good subset, a big subset of these kind of problems. So think about transportation. Think about, in fact, think about movement of people and goods through a network, any network. It could be a transportation network, it could be a port, it could be airlines, it could be cargo, it could be a supply chain, it could be stuff moving between facilities, Amazon operations, all of this. All of these are great examples of problems that fit really well with the quantum technology we have today. And it is proven that we can gain advantage. We can solve them better. We can save money. We can increase productivity using quantum computing for these kind of problems. Now, these are not the only kind of problems. Scheduling is another one. Okay, so workforce scheduling, machine scheduling, operations scheduling, or generally managing your operations. I mean, ultimately in your operations, the key factors are time and money. Right? So any operations you run, key factors are time and money and human resource. How much human resource do you have? And those, optimizing them and getting the best value out of these resources, that's an optimization problem. Okay, irrigation, agricultural productivity, all of these are examples of optimization problems. There are a couple of other classes of problems that quantum computers are really good at. One is synthesis problems. If you want to create a new material, the best new material for batteries, big research is going into how to increase the capacity and the longevity of batteries, which basically means synthesizing the next molecule, the next material for batteries. Coming up with the next best drug, for cancer or any other condition. Reducing side effects in drugs, creating a new small molecule or large molecule. Okay, so those kind of applications quantum computing excels at as well. Okay, so those are the two. Our focus today is going to be more on the operations, because I wanted to keep it general so that everyone can relate with the applications. But there are some very deep scientific applications as well that you can find. I'll give you the resources how to find those problems. And then, of course, we're living in the age of AI. So what is the complement between AI and quantum computing? There is a very strong relationship. With AI models, you can train them, you can get them to a certain point, where you'll get an accuracy of, depending on the use case, you'll get 95%, 92%, 89%, somewhere in that range. And then you'll reach a point where doesn't matter how much more data you put into it, or how much more training time you put into it, you just cannot increase the accuracy anymore. The model will overfit. It'll lead to some other issues. So you plateau in terms of your model performance. So when you stop, when the traditional AI approaches where they end, that's where you can bring in quantum computing and optimization techniques to increase the performance of AI models. So those who are in the AI field would know that underlying every AI model, there is a problem of feature selection, and there is a problem of hyperparameter tuning. Those are optimization problems, which typically are solved in a approximate way. No one really focuses on solving them deeply. But if you do, you can actually increase the accuracy of the model or reduce the error rates. And this is where optimization and quantum computing. So these are things where Super is already very good at. You can do all of this with Super. Now, there are other things which are near term, which are coming to Super. Okay. So one big one, which concerns all of us, actually, is post-quantum cybersecurity. So there is the good side of quantum, and then there is the issues that it will create as well. Once quantum computing reaches a certain scale, our internet security, all securities, all passwords, everything will be compromised. unless we switch to a different protocol. Today, our whole internet security is based on the principle that it's hard to factor numbers. I mean, 12, the factors are 4 and 3, and then 2 is a factor of 12. That's easy. But if you take a really big number, finding the factors of that number is a big challenge. Take a number with 1,000 digits, and try to factor it. It's a hard problem. Okay. Unless there is a 0 at the end, 2 at the end. I mean, you put an odd number at the end and you see it becomes an extremely hard problem. And that's what our security is based on. That's it. That's the principle. Quantum computers can factor fast once they reach a certain scale. So all of our passwords, all of our encryption, everything will go through, go to the bin basically at that point. So what we need to do is we need to proactively move our systems to post-quantum secure encryptions. Now, those encryptions exist. It's not that they don't exist, but enterprises and people are kind of oblivious and they say, okay, it's fine, quantum computing is not there yet. We're okay. What we have to realize is that hackers are not waiting for quantum computers to reach that scale. They're already gathering information. It is encrypted information. They cannot use it today, but in a year or 2 years or 3 years or 5 years from now, they will be able to break that encryption. They will be able to use that information. And the data which is sensitive today, a lot of it will remain sensitive in 5 years. Think about it. So the threat is today. The threat is not a future threat. It's a today threat. And it's bizarre why we're not taking note of this, or why governments or big enterprises are not taking as much note of it as they should be. It's a huge issue. Okay, so we're bringing, this is something we support in SuperQ right now through our professional services, building these protocols. But in Super Platform, we are introducing this capability as well, that you'll be able to give it your requirements and it'll build you a protocol that will protect you from these post-quantum threats. Okay, so start thinking about that right now. Yes, it is, because we understand quantum computing, we are able to create a defense that quantum computers cannot breach. So it's not quantum computing that will create the defense. It's the understanding of quantum computing, which will lead to a defense mechanism. No, that's a good point. You can. So and actually you can Google it. There are post-quantum secure protocols available. There are, not very easily. That's the part. How do you implement? How do you commercialize? There is a friction. There is a friction. There are certain blockchains. So those who are in the crypto space, there are certain blockchains that claim to be post-quantum secure. Some of them are. Some of them are half secure. Some of them are. I think none of them is fully secure, but some of them are half secure. So there are these protocols that do exist. It is a challenge to implement, and that's what we want to simplify through Super. Okay, so that module is going to come to Super as well, and then finally the big piece of R&D that we're doing, which is where we have made some progress already. How can you train generative AI with less data and less computation? Because the energy footprint of AI is a big concern. The data footprint of AI is also a big concern. We're running out of data, actually. OpenAI has used all the data in the world, pretty much, to train. And now, basically, they will be training based on AI data. Okay, not human data. Human data has run out. So what is that going to lead to? Okay, so there is a real concern that if we want to increase the performance of our models, we have to look elsewhere. We cannot just keep relying on more data. Okay, and then how do we do it? You try to replace how GPUs are used in training AI with quantum processing units, QPUs. Okay, it's challenging. It's not easy. It's not going to replace GPUs completely, but it can reduce the use of GPUs and data. And that's the active area of research, which can save potentially millions of dollars. Like if you think of ChatGPT training it from scratch today, and if you were using a hybrid approach, QPUs and GPUs rather than just GPUs, you would be saving something like 100 million. Okay, which is a lot. So yeah, that's the active R&D area. Now, before we do a demonstration, I want to walk you through some concrete examples and case studies. So you can start thinking about it. What are the kind of things you can solve with super or with quantum computing in general? Okay, and I'm going to focus on these cases, the ones I had on the previous slide, the optimization cases, okay, and the AI cases. Okay, so let's see. Okay, this is the first one. So each of these case studies is backed by data. So there is some customer that has already implemented, and they have got an ROI, and it's easily findable on the internet. It's all documented on the web, so you can verify the story. Workforce scheduling. That's a bread and butter problem for super and for quantum computing. Pretty much everyone needs it. Every business needs it. The bigger the business, the more operations there are, the bigger the scale of the problem, the more saving you can get by using quantum computing, or using, even before quantum computing, using proper optimization. Okay, so problem is that we're not even using the classical stuff properly right now in industry. So the benefits are there. I don't even have to go into the benefits of what it can unlock in terms of benefits, but I'll talk about the concrete case study, and it's a case study that's accessible to us. Save on Foods. Okay, it's a grocery store. You wouldn't think they're using quantum computing, but they are. They are using the quantum computing for their delivery scheduling, and they are not the biggest delivery operation in Canada. They're pretty small compared to other operations, but they have seen a major return on investment by scheduling and organizing their deliveries using quantum computing. Why did they do that? The issue is that they come up with schedules, they come up with delivery routes and everything, and then 10%, 20% of the drivers don't show up. They're sick, not showing up for whatever reason, and they have to ship stuff. What do? They were randomly assigning stuff to other drivers. Not optimal. Losing money, losing time. Now what they do is they run the job on a quantum computer. They get the result in minutes versus hours that it used to take them to regenerate the schedules. So before they couldn't wait for the new schedules to generate. Now they can wait. In a few minutes they can generate. And then they can assign the proper jobs to the drivers that are available. And doing so has given them enough ROI to run this every day. Okay, so very accessible use case. Any sort of deliveries, any sort of movement. So it's a dual problem. It's not just scheduling. It's scheduling plus routing, both combined. Okay, so highly documented case study. This one, you can find a lot of information about it. It was done using D-Wave's computers. So this is a D-Wave case study, but the same technology and more is available through Super to enable this use case. It took them months to do it, or close to a year to do it. Through Super, you can do it in days. Okay, that's where we are at right now. And some metrics, how much was saved, and you can find more information about it online. It's very well documented. Patterson Food Group is the company behind Save on Foods, basically. Second one is a triple use case. So I kind of bunched them together because the underlying technology is similar. Okay, it's basically how can you run movement operations? You're moving something in a network. How can you optimize that? Now the movement can be through a supply chain, through an irrigation network, through a utilities distribution grid, or through a factory floor. Anywhere where you need to move things between different machines, different people, different facilities, it fits in this bucket. And there are three examples that I'll give you under this bucket. One is very, very simple example: tour planning. There is a marketing company, there is a tourism company that plans trips for a large number of people through different destinations, and people want to go to multiple places. They go to one and then the other, and you want to optimize, you want to reduce costs, you want to make sure that you get a healthy margin. How do you do that? How do you manage this movement? This is a classical example of traveling salesperson problem. So those who are in the computer science or in the technical space would have heard about traveling salesperson problem. This is a version, this is a general version of that problem. And quantum computers are really good at solving this. This is one of the perfect fits for the technology we have today. Okay. Port operations. Ports are the best places, best examples, because you have complex operations, you have movement of goods, you have scheduling happening, you have routing happening. It's the convergence of all movements of goods. Okay, so port is the ideal use case for quantum computing. And Los Angeles Port has implemented quantum solutions for their operational optimization. TP World, which manages several ports around the world, they're actively engaged in exploring quantum computing. Okay, so think logistic facility. So even if you go down from a port to a logistics facility, that there is significant ROI in using quantum computing. Third is manufacturing, any type of manufacturing. You have factory floor, you have different machines, and one machine does part A, second machine does part B, C, D, and then you need to schedule. You have finite resources, you have finite machine hours, and then you need manual labor, you need some man hours, and you need to figure out how to optimize, get the best productivity from the resources you have. Ford Otosan had this problem. Okay, so they manufacture vehicles, and they have a big repairs operation as well. So this particular example, I think, is for their repairs operation. So the way the repairs work is that they have different crews and different machines, and they want to maximize their utilization and minimize their latency. They don't want a machine or a person to be free, or waiting for too long. They don't want them to be overworked. Okay, and they can predict the demand, but not exactly. So the demand is variable. Okay, so how do they optimize? They are using quantum computing today, and they have seen significant ROI. This was one of the shining examples actually in the last Qubits conference, which is a major quantum computing conference. This was the main new use case that was presented. Okay, so all of this is completely documented, and you can see the results by just doing a Google search or a Perplexity search if you're more into AI. Okay, and then the third one relates to AI. I already talked about it. The energy footprint of AI is a huge concern. How do you reduce it? So we're not there yet where we can reduce it a lot today, but we can make a difference already. You can, for example, improve the performance of your RAG models. So there is a thing in AI called RAG, Retrieval Augmented Generation, RAG. So in AI, usually when you try to build a AI agent or your own AI application, either you use fine tuning or you use RAG or some approach in between. So RAG is something where you give it a knowledge base, and it's supposed to use that knowledge base to answer questions. And there is an embedding problem there, how do you embed that data into the AI model, not into the AI, but into the database. And then how does AI use it? So that problem you can optimize today. And then the goal is to be able to optimize the training of large language models, which is what we are working towards. Okay, so that's going to be a massive one moving forward. Okay, and then okay, so now let's talk about productization. So case study is good. We talked about use cases, and I hope that this gives you a good understanding of the cross section of things that are possible with quantum computing. I didn't talk about any drug discovery stuff. I didn't talk about any chemical synthesis stuff, because that gets technical. But keep in mind that any sort of material synthesis is a good candidate for quantum computing as well. Okay, and I can give you those case studies. I mean, you can do a search. Actually, IBM has several of those. IonQ has those case studies, and D-Wave also has those case studies available. Okay. So now let's talk about some productization. So I want to show you stuff. Okay, and before I show you Super, I want to show you some commercial stuff that we have built where we have productized quantum computing. So you can see how productization looks like. Okay, so one of the main catalysts for some of these productizations is our partnership with D-Wave. D-Wave is a close partner of ours. We signed the deal last year in September, and it's a multi-level deal. It's commercialization, technical collaboration, all kinds of stuff, focusing on North America and the Middle East. But now it's even expanding from there. We're looking at Asia and Oceania overall, plus North America. Okay, so and we have a partnership with NVIDIA as well. So today I'm focusing on quantum computing because the title of the master class is how quantum computing can do business optimization. But there is a whole other or much bigger world where high performance computing or classical computing can enable things just as well. And all the solutions I'm talking about here are hybrid solutions. They all have some component of classical high performance computing and some component of quantum computing as well. So this is a big catalyst. And what has that achieved, this partnership? This is one of the shining examples of what we have been able to achieve. It's a fully productized solution. It's a customer facing product, which is highly unusual in the quantum world. If you look at the quantum commercial use cases, nearly all of them are for a company's internal use. Ford Otosan is using it for their internal optimization. They're not making quantum available to their customers. This is an example where a product was built for one company, but their customers are using the product, not that company. Okay, so Verge is the company. Verge is a precision agriculture company. Some of you would know Verge. It had its roots in Lethbridge as well, actually. So it started in some form, an early form of it started here, and now it's a multinational company, but not a huge company. I mean, it's a Series A company. It's decently big, but not like a big enterprise. Okay, they had a need coming from agricultural research and government bodies. Those bodies wanted to understand the impact of using robotic machines in agriculture at scale. So PAMI, who knows about PAMI? Saskatchewan, PAMI. So Prairie's Agricultural Machinery Institute, okay, very well known, very old institute. They do research on agricultural machinery. They wanted to understand the impact in Saskatchewan, over 25,000 fields. Grain Research and Development Corporation Australia, they wanted to understand the impact using robotic machines in Australian fields. And there are many questions there, many research questions there that need answering, like soil erosion or, compaction and productivity increase if you switch to autonomous machines, and what size of machine is good, section control. There are many questions there. But how can you even perform that study? Because doing that over 25,000 fields is a challenge. You're basically deciding machine routes over thousands of fields. And routing is a hard problem. Okay, routing means that you decide how the machine is going to go from point A to point B, how it's going to cover the whole field, how it's going to go around the obstacles, how it's going to turn, where it's going to turn. Okay, so all those decisions, those are tough decisions, and you'll see why they're tough. I mean, I'll show you a video which shows you why it is tough. To solve this problem, we integrated quantum computing into Launchpad, which is the Verge product. And it is productized, and it was presented at Qubits, and their customers are using it. Okay, this project was invested in by Digital Supercluster, which is a major Canadian federal funding body, and they called it world's first customer-facing productization of quantum computing. Okay, so let's see what this is actually. So I think there is a video on the next slide. Is there a video? Do you see a video link or? Oh, okay, here we go. Okay, perfect. So this is what I presented at Qubits, which is a major quantum conference. The Launchpad, which is Verge's product, logged in, and you can see the URL, it's app. It's not demo, it's not staging, it's not tests, it's app. This is production environment, okay? So what I'm gonna do, I'm gonna run a demo with 50 fields. Okay, so we ran it with, we have been able to do tens of thousands of fields, but for the interest of time, I'm gonna use 50 fields. So it used to take us 10 seconds per field to generate a route for these machines. which means for 50 fields, it would take us how much, 10 minutes, close to 10 minutes, 8 to 10 minutes to generate this. But you'll see here, hopefully, that we will be able to generate it in 1 second per field or less. So we'll get the results in 50 seconds. And then I'll explain to you what the results are, what do they mean, and what are the complexities, why this is a problem that's hard, and it required a quantum solution. Okay, so fingers crossed. I'm gonna run this. Okay, so routing. Start counting. Okay, 50 seconds or around 50 seconds. There is some overhead, for the systems to communicate with each other and results to come in. On the quantum machine itself, it takes less than 10 seconds approximately. The rest of the time is communication. So those of you who are thinking about productizing quantum computing should think about those aspects as well. It's not just the solver time that matters. It's how the systems communicate with each other and all of that comes into it when you're productizing something. So we wanted to get a productized time of 1 second or around 1 second. We were hoping for 2 seconds, but we made it to 1 second. And this is only 4 months into the project, and we still have a year and a half to go on the project. So I think by the end of it, we'll have even. Oh yeah, it's done. Okay, I kept talking. Anybody kept track? Well, I'm happy, So it's done. It's working. Cool. So, but what is it? What did we do in these 30, 40 seconds, whatever we did? We have generated machine routes for these 50 fields, and they are color coded. So basically the green point is the start point, the recommended start point. The red point is the recommended end point, and the arrows show you how you go from green to red. Okay. Seems like a simple problem, like what's the big deal about it? Why is it a tough problem? I'll show you why it is tough. So I'm gonna go to, let's go to this field, okay, and I'm gonna zoom in to this field. Okay, take a look at this one. This is a field with some obstacles, some holes, so obstacle means maybe there is a tree there, maybe there is a pond there, so you're not farming there, you're farming around it. And you want to farm as much of it as possible around it. So you have these loops. So what growers do, those who are familiar with agriculture, they do a perimeter pass of the machine around the field. Then they do perimeter passes around those obstacles. So they do loops, okay? And then they do passes, up and down, or left, right, whatever, whichever direction they want to take. This is how you get these tracks. But now we want to make a route from a start point to end point. So there are two issues here. One is you need to decide which track do you go to next. When do you do the loop? When do you do a loop around obstacle 1, obstacle 2, obstacle 3? Okay, and how do you do it in such a way that you minimize your distance or time? This is, for those who are familiar with computer science, this is kind of a traveling salesperson problem. Because you're navigating a bunch of tracks and minimizing your time, and there are some agricultural constraints that you have to meet as well. That's why this is complex. It's an NP-hard problem. Okay, and we're solving 50 NP-hard problems here at the same time. Okay, and in a very short period of time. So I'm going to run the simulation, meaning I'm going to run a slider here that shows you how the route actually looks like. And you'll see it's highly non-trivial. Okay, let me start this. So the recommendation is you do the boundary pass first, the perimeter pass. Then you go to a track, you go back. Oh, this is interesting. Look at this. If you look at any major agricultural OEM system, they would tell you to go to the next track. Do the first track, go to the next one, then go to the next one. So nearest neighbor, go to the nearest neighbor. But that is not the best solution. This is highly non-trivial now. You're going like you're skipping 4 tracks, going somewhere else, doing a loop around the obstacle, and then you continue. Oh, you skipped another 2 tracks. Oh, now you went back and forth, back and forth, back and forth. And you're not just randomly going back and forth. You're always trying to use the track or the pass you already generated, because you want to minimize the wheel traffic in the field. You don't want to erode your soil. Okay, so you latch onto the perimeter passes to go back and all of that stuff. There's a lot going on here. But what you can see is that this is highly non-trivial. And this is the part the classical computers, struggle with. You can use a classical optimization solver to do something like this, but it'll take you a long time. As I said, 10 seconds. Okay, so this is how the productization looks like. It's available through a web app, everything. So on the front of it, you just see the results. But underneath it, a lot is happening. And a component of it is being solved on quantum machines. The rest is being done on classical machines still. But this ordering and this route ordering problem, that is being solved on the quantum machine. Okay. So great use case, routing, scheduling, movement of goods, great use case. Okay, so what do we, okay, so now that we have seen a productized version, there are a couple of others as well. I mean, there are several others, but couple which I wanted to highlight here. One is related to AI. Okay, so Science and Humans is a telehealth company that's based in Ontario. They have global operations. They have tens of thousands of customers, and now they're hitting hundreds of thousands of customers. So they first came to us. They came to Stack, which is the AI company that I'm part of, to build AI clinicians, because their human clinicians couldn't keep up with the demand. Okay, and now once we build the AI clinicians, the same issue. You reach a performance level, and that's it. You cannot go beyond it, no matter how much more training you do. So how do you go beyond it? Because life sciences, it's a sensitive application. You want to gain as much accuracy as possible. So now we're bringing in quantum computing to enhance the performance of AI models, and that's another major project that we are undertaking with them. So Super is a part of it. Super is playing a key role in this, but there is some stuff that's our professional services are doing as well on this. So you'll be hearing more about this use case soon, and a productized version of this use case soon. Another one is actually a Dubai-based company, Neurao, which is investing in brain-computer interfaces and doing so very accurate. There are these EEG headsets that you can use, which can detect signals from your brains and convert them into commands, but they are not very good. They're noisy. And noisy meaning that you may be wanting something else and it will do something else. And the reason is the channel selection part, like what channels from the EEG headset should be used for decision making. Now that's an optimization problem, which we want to optimize using quantum computing, which will then enable some key use cases for health and wellness and brain activity monitoring and so on and so forth. Okay, so those two will come soon. You'll see some information and some productized versions of these coming out pretty soon. But there are videos about them already. There are case studies about them already. So I'll spend a little bit of time on this before, and then we jump into the demo. I think Krishna is waiting patiently for his opportunity to show you Super. But underneath Super, there's a lot going on. Our secret sauce is what sits on the top. How do we break a problem down and figure out how to solve it, where to solve it, which part to solve on classical machines, which part to solve on gate-based quantum machines, which part to solve on quantum annealers. There are different kinds of machines with different strengths. Okay, so that part of decomposing a problem and figuring it out is our secret sauce, and that's the patent pending part. Okay, underneath it, you have all the best hardware and solvers in the world. Okay, so you have IBM's technology, you have Google's technology, you have D-Wave, IonQ, NVIDIA, everything is there. So you don't have to go to one vendor, you can use all of it under Super. Okay, so I'll end this part here, and time for a demo. So Krishna, you're there? Or are you asleep? He's in Dubai, so...
Not yet, Mohammed. I'm sleeping. 10:45.
Okay, it's very early for you. He doesn't sleep, so it's all good.
Okay, great. Can you guys hear me? All good?
Give a bit of an intro about yourself, where did you come from? Why are you here? Why are you up at this time and doing this, Talk about it.
I'm here for the demo. So, hey guys, my name's Krishna and I'm the Chief Operating Officer at SuperQ. My background has covered a lot of optimization, machine learning, generative AI, blockchain. So pretty much done most of it. or pretty much done most of the trends over the last 4 to 5 years. I was at EY where I was leading their generative AI and supply chain applications. And before that, I was leading their forecasting applications as well. So that's a quick one about me. And I hope everyone can hear me well just before I start the demo. Mohammed, is everything good on the
Yeah,
audio
everything is
side?
great. On which I did not expect. Your internet is always dropping. Today is good.
Yeah, let's hope it doesn't drop during the demo. So I'm just going to share my screen and you guys can let me know once the request is there. Good. Okay, perfect.
Charlie, are you seeing his screen or?
I hope everyone online can see my screen as well.
Yeah, it's there. And you can turn off your video if you want to save some bandwidth. It's up to you.
Yeah, I think it'll be good, Mohammed. So I'm just going to quickly log into the platform. And how I'm going to try to structure this demo essentially is one, I'm going to walk us through some of the use cases that we solved through Super first. And then I will also walk you through like how you can input a problem in and solve a use case live during the call. So what you see right now is the Super UI. I unfortunately can't use dark mode because I think Mohammed says people can see it better. It's a light mode, but this is scarring my eyes. So what you will see over here is the Super UI, pretty similar to ChatGPT, but obviously there's a lot happening over here. So I'll go through it bit by bit. So the way that you can start a problem is you can either start it from scratch, where you put in a research paper, you put in any problem that you might have, which is complex, and you can analyze the problem, fine tune it a bit, and build your code from there. Or else you can augment an existing solution. So the augmentations that we do support now is where we have a classical solver called Gurobi, where we can potentially convert it to, let's say, a quantum annealing code. And we can potentially weigh in, like, does your problem actually require quantum now, or is it fitting the current classical mandate that's happening? And it kind of gives businesses a view on, like, do I need to actually use quantum, or is my classical solver actually doing my job? What we will be enabling post this would be more on the other classical solvers from IBM, like Cplex. Then we can optimize machine learning models as well. I think Mohammed had mentioned that there's more deeper machine learning optimization problems that come in. So that's going to be there, where we introduce generative AI models as well as normal AI models that come in. So I'm going to pick a problem that we solved. Just before that, I'm just going to show you some of the example problems we have. Typically, we're covering all industries right now. There's manufacturing, logistics routes, carbon emission optimization for flights. That's a pretty interesting problem. For the financial sector, we have portfolio allocation and portfolio management, adaptive supply chain optimization, airline prep crews. This is for all those people who have been delayed by their flights. So this is something that every airline/airline hub can use. Clinical trials is something more on the pharmaceutical side. Semiconductor fabrication is again a manufacturing related problem. Machine learning models. I'm pretty sure all of you know the tariffs that are coming in. So how can maybe you, being a US supplier or someone that is supplying to the US, how can you optimize your sourcing to ensure that you don't fall under the purview of tariffs? Energy generation is pretty important because as countries and other people move into more sustainable sources, how much energy is needed to power a city or a town or whatever that could be. And we have mobile network as well as data center jobs. So the particular problem that I'm going to pick right now is the clinical trial optimization. So as we know, load this particular screen is called a super notebook. So a notebook consists of multiple elements. So you have your chat with the AI, you have the generated code, you have the solved problem, as well as a prioritization / visual input for business users to consume. And what we can see from here is that, there's a number of things happening on the screen. So let me take you through it bit by bit. So first thing is, what is the problem trying to solve? So we can click this analysis screen and we can see what the problem is. So a problem definition is a pharmaceutical company has a set of drugs, which is for phase 2 clinical trials. And their single overriding objective is to minimize the expected burden of side effects per drug. as well as ensure that there is an efficacy percentage of 80% on each arm, as well as remaining under $6 million of budget. So you can think of it as three objectives that have to be uh, achieved through this problem. And from here, what we can see is that, all the data is input with the problem, and we can see that, what is the ethical requirements. We can see what are the exact inputs, the cost per participant, etc., etc. And you can either upload in your data in line with the problem itself, or you can potentially even supply a separate data file, like it could be a JSON, it could be a CSV, it could be an Excel file. And what the underlying AI agent would do is it would try to assume and see that, what is the input points, what's the output points, and so on. And what we are able to see, the feasibility that has come in, is that we can see that it's a particular constrained integer optimization problem. And what we can see is that the approaches that our underlying agents have come through with. So we can see that the two main approaches are hybrid CQM as well as a CQM. So for people who do not know what a CQM is, it's a constrained quadratic model, and it is a particular solver under the D-Wave architecture, under the D-Wave hardware, which kind of helps you solve a problem through a type of mathematical equation. So it has given us both options. And what we have done is we have picked option number one. And from there, it has generated a solution for us. So the running joke, or rather the running timeline to solve this problem, what I at least have proposed since I'm the head of product at SuperQ, is that we can go from problem statement to solution potentially in 7 to 8 minutes, which is something I do stand by, so that I potentially can run a timer for you while we run a new problem. But what you can see over here also is a number of agents that are essentially working together. So you can see that there's a code judge, there's a code helper, there's another regenerate agent that comes up if your problem's not solved. There's a productize agent. So what these are different agents kind of working together, but are independent from each other. So what it means is that the agent that generated this code is not going to be the same agent that judges the code. Because it's pretty much easy to say that, oh, I can toot my own horn and be like, oh, my code is great, it's the best thing in the world. But someone else who is potentially more experienced can come in and be like, hey, your code's not pretty good. And that is a problem, which I did not see. But that potentially could have an issue over here. So from there, what we can potentially see is the solution that has been produced, which is, I'm going to potentially view a productized solution. And what we can potentially do over here is see that, there is a certain objective that a business user can see. So from here, we can see that there is some budget utilization that has been assigned, which is around $6 million. But you can see that the only amount that was totally spent was around $4.3 million. Well, what this means is that, there is a reduction of costs of around 20-25%, which means that we don't spend our whole budget. And we can see that there is increasing efficiency across different arm performances. And we can see that we have achieved active arm statistical power of around 80% across each arm. So we can see that all of our objectives are essentially met through the problem itself. And we can also see the fact that there are different definite business objectives that are being accomplished. And this was something that took our team potentially 7 to 8 minutes to come up with a full solution. And we can see other metrics over here like solver performance, how many milliseconds. So this you see is like microseconds. So this is how many microseconds it took to solve the problem on the quantum side and how many qubits it took. What we see on the left over here is something that we can modify ourselves to rerun the problem and compare how it goes. So for example, let's say our budget increases to maybe 10 million, we can potentially change that and see how much it looks like. Or maybe we can go back into the solver itself and...
Krishna, can you do the employee scheduling one from scratch? So after you're done with this.
Yeah, perfect. I'll do that. I think I'll just have to put in some credits, but I'm just going to pause during that time. But let me just stop sharing my screen for a second. Give me a second, guys. I'll just get back in. Mohammed, you can potentially walk them through it while I just do a quick check on something.
Okay, sure. So basically what you saw just now is what we call a super notebook. This is the end result of going through the process. Krishna hasn't shown you the process yet. He's gonna show you how a super notebook gets generated in 5-10 minutes, basically. But what it is you give it a problem, it analyzes it, it first fine tunes the problem. So you'll see that it'll work on the problem, improve it, ask you questions about it, get the problem to a point where it's properly defined. So you don't have to worry that are you missing something. It's going to help you. The platform is going to help you get to that point. It's going to ask you for data. It's going to ask you for inputs, constraints, requirements. After which it'll figure out how to solve it. Should it be solved on a quantum machine, on a classical machine, or on a combination of the two? Okay. Once it figures it out, then the coding agent comes in that builds the code base. And there will be errors. That's why we have the code helper and the code judge, because you run the code, you'll see, oh, there's some issue. Now, you don't have to be a coder to fix it, because we have provided the tools within the platform for that. So you just focus on your problem and let the agents help you in the platform. They will take care of it. Once the code is fixed, it is deployed, you'll get results. So if you're a technical person, you can work with the technical form of the results, which is a JSON format. Those who are in the computer science know what is JSON. But if you're not, you just skip that part and go to the productization, which will then generate a dashboard for you, where all of your results will be visualized. And that dashboard varies from problem to problem. It's not a fixed dashboard, because every problem has different objectives and different goals, right? So it is being generated on the fly by another agent based on the problem. And then on the left side, what you saw was the sliders where you can change the inputs of your problem and run it again. So effectively, you get a productization. If you build a solution like a scheduling solution that works, you can keep running it over and over and over again. And if you want to integrate that solution into your existing systems, you would use an API. So we will expose an API through Super, which will then integrate into your systems. So you wouldn't even have to use the platform. Once you build the solution, you can consume it anywhere. Okay, Krishna, you're set?
Yeah, all set. Sorry about that, folks. Had a bit of a admin problem where I ran out of credits for that. So I just did some backend magic and a bit of auto-tune potential to get that fixed. But let me pick up a problem that we have pretty much solved pretty well. So I'm just going to pick it up from here, which is an employee scheduling problem. So I'm just come over here, copy all of this data in. There's a very annoying Zoom pop-up, so you can see me moving my screen around, but just gonna copy that and come back into Super, and we're good to go. Yes. So what you can see over here also is the typical format of an expected problem. Like you can see the structure, the background, context, decision variables, objectives, constraints, and the expected output. And the reason why we have this guidance is that we want to ensure that there's no form of garbage in and garbage out. So that, people can be like, oh, the platform's not working as well. But I think that the main thing is that you need to define your problem pretty well so that the platform complements the problem. This problem also requires some additional data, which I'm going to input in. And this is a preview of the data we're using. So AI has picked up what is the data, what is the shifts, and we can see like what's the type of data as well. All of that passed pretty quickly. And step one to this is essentially fine-tuning your problem. So I've just started a quick timer on how long this is going to take, but let me fine-tune the problem statement. So these might look like buttons to you guys, but what this essentially is different agents working on the problem statement independently, like I had mentioned before. And what the step one essentially is to ensure that your problem statement's pretty straightforward and you have a good enough problem statement to solve. So you can see that over here, some issues that were identified is that, data details is referenced in an attached file, but could be more explicitly integrated as numerical values. And objective functions and constraints, while mentioned, could be clarified further. So we have some enhanced problem statement over here. We have the old one as well. And we will use the enhanced one over here. And then the next agent is analyzing the feasibility. So step two in getting your problem statement out is essentially analyzing which hardware or which provider would be the best suited for this problem statement. So as you know, there's like, GPUs, there's CPUs, there's quantum computing providers, etc., etc. But essentially, we'll have to see what is the best provider for this particular problem. And what this agent also does is it kind of asks you clarifying questions to kind of help you better get a problem statement answered up. So over here, you can choose to ignore the questions as well. And it'll be like, assume it to the best of your abilities, but it's better for us to actually give an answer. So for the shift coverage constraint should be equal to the required number. Is it acceptable to have overstuffing? So no overstuffing is allowed. Beside maximizing fill slots, are there any other objectives? So for the sake of this, I'm going to say no other objectives. And lastly, in case where employees availability or maximum shift prevent full coverage, should the model flag these shifts for manual review, or is there an alternative secondary objective? No other secondary. So adding this back into my problem statement, you can see the decided over here, and I will reanalyze the feasibility. So model takes this back in, kind of tells you that, okay, most of these questions are answered, and it will try to come up with potentially what could be the hardware that we use to build out the solution. And like I was saying, it goes through the number of hardwares available on Super right now and kind of comes up with like, okay, this is going to be the best for this. Like if you put in a machine learning problem, it's going to be like, oh, you can use a GPU and you can deploy it to cloud-based GPUs. If it's something related to optimization, to use a D-Wave annealer. And if it's something related to classical compute, it would suggest Gurobi. So here we can see that, what type of problem it is. Like I'd shown you the feasibility analysis screen earlier. And we can see that, it has suggested something to us. It has either suggested Gurobi as our first option. And we can see that D-Wave is second because obviously quantum might be overkill for this. And we can see that, the reason why it has suggested such an option. So you can see that expected performance, high performance guaranteed with guaranteed optimality, extremely reliable. And what we can see is that it's a simple problem and it is saying it's telling us to use a classical solver, but I'm going to try to be as overkill as possible and potentially use a quantum computer to solve this simple problem. And I'm going to generate the solution. So it gives us a choice of hardware. And obviously, for someone who is not too familiar with the platform and the solvers itself, the primary one is potentially the most used one. But since today I am slightly more experienced on how Gurobi works and how D-Wave works, I've chosen D-Wave because we can see how fast the solution is generated. And this would be more on the research side where, people can potentially weigh in different options. And what Super also allows you to do potentially will be for you to run this across Gurobi and D-Wave and test out and see how both work. And then going forward, you can choose which solver would you use in a production environment. So having this comparative analysis is what Super also allows. And you can choose what's best for you and what size fits all. And as we know, no size fits every problem. You can use each solver however you want to, and that's how it would work. And we can see that the code is generated, pretty simple code. I wouldn't say pretty simple code, but I'd say it's pretty large code. And I will deploy this to the annealer. Fingers crossed that it generates a result. If not, I will go off screen again. And let's wait for a couple of seconds. And oh, perfect. That generated a result, which was pretty unexpected. I'm just kidding. But what you can see over here is the solution that it has given us. And from this solution, you might be like, what does E10 Friday morning 0 means? And that's something where our productize agent kind of works on its toes and tells us that, this is going to be the best visualization for this. So I'm going to click on the productize button as well. And while that generates a visualization, as Mohammed was saying, this is purely generative UI, where AI potentially picks out what's the best view to visualize how you can see the solution being built. So think of it as if you're a finance person, you probably want to see a graph of how your portfolio is being optimized and how much money you have to allocate. But if you're someone who's working on the scheduling side, you want to see what time you want to put in your schedules. So these are two completely separate visualizations, and we can't have fixed visualizations showing one person the other visualization. So what Super is doing is it kind of builds out your visualization and gets to the point where, each person sees the exact visualization their problem's actually showing. And it kind of also lets you build other visualizations as we go on. So potentially you could also walk into Super and be like, can you build a visualization to show me this? Or can you do that? So all of that is embedded within Super itself so that you can exactly get the decision you're trying to make. So for the clinical trial one, the main decision was reduce budget, 80% efficiency. And we were able to see that there was a reduced budget and there was 80% efficiency. So that's great for us. And moving from there, it's as decisions as they go in. And just over here, I think from the problem start to problem end, 6 minutes, 30 seconds. So I'm going to stop that timer. And again, like I promised, sub 7 minutes is how much it takes to solve like a small scale problem, obviously. But you can see how the staffing is working. Like you can see that Monday morning, there are, 2 people required, 2 people assigned. Monday afternoon, there are 2 people required, 2 people assigned. And we can see that all shifts are filled equally. Obviously, you can see this graph where it shows us how much each employee has been assigned. Employee number E1 probably got the short end of the sticks because he has the most amount of shifts. But E8 probably has only 1 shift, so potentially could get fired. I'm just kidding. Don't take that seriously. But you can see how the shifts have been filled and you can see the utilization of each employee as well. And what we can do over here is we can increase the number of shifts. We can increase the number of employees per shift. We can put it as 3, 4, 5, whatever it could be. And we could get different results and we could compare it with the original and be like, okay, these were the different results. This is how I can keep changing it. Tomorrow morning, someone could come in and be like, hey, I'm not coming to work for the next 3 weeks. So potentially people might need to be intimated to do more shifts. So that's something that can be done as well. But yeah, I think that was my demo. 7 minutes, as I promised. And
thank you, Krishna. I really appreciate it. By the way, are there any questions on the platform? While Krishna is here, we can ask those questions. And then there are a couple of slides I'll go through as well. Yeah. Probably need the mic, otherwise he won't hear you.
Yeah. Hi, my primary question about really the whole thing, but also this platform specifically, is it only used against traditional GPU computing in cases for optimization specifically? Like, can quantum be utilized for use cases outside of optimizing the solution to a problem, if that makes any sense whatsoever?
So typically you would need quantum computing's help to make a decision. So you want to find some answer to a problem. A lot of those problems end up being optimization problems, but not all. There are so those who are in computer science, there are search problems, there are decision problems, there are optimization problems. We kind of broadly speak about all of them as optimization, but you can solve all 3 types using Super. Now, are there things that are outside the realm of this that Super will not be able to solve? Yes, that can happen. You can bring a problem that is highly subjective, doesn't have any data or any sort of decision variables attached to it. What's the purpose of life? Those kind of questions, or more questions that are more nuanced and cannot be encoded in a mathematical equation. That can happen. That can definitely happen. But most decisions that we are interested in as a business user or as a researcher can be encoded in mathematical equations, and they can be cast as a decision problem or optimization problem. So that's what Super is good at. Now, it won't be able to solve everything. It will run into issues, of course. It can say that, okay, the existing hardware or solvers are not the best for this, and there's something coming later, or, potentially there isn't anything which is a good fit for this problem. That can happen.
Just to clarify a minor point there, oh my God, they passed me the mic and the thought go away. I'm so sorry.
Okay. Any other questions for Krishna particularly? For me, I'm around. You can ask me afterwards as well. Oh, okay. Krishna, are you able to see the questions?
Krishna's answered one of them there for us, which is great. But there was one at the bottom here. Grok has announced a multiple agent AI product. Would Super enhance Grok's capability?
Krishna, what do you want to say to that?
There's a lot of things I could say to that actually.
So not right now. So I would say, okay. So when we are supporting training of AI models, like large language models, at that point, yes. But right now, Grok is a large language model, and there are agents built on top of Grok. That's what OpenAI, Grok has released to public, and not much you can do because the model is pre-trained. Like we cannot optimize it. But in future, yes.
So just to add on to that, if Grok was going to do Grok 5, we could embed Super essentially during the training process of Grok 5 to to make a number of changes around the generative AI value chain. Because right now, I think that when you try to break down generative AI training, there's multiple problems that start right off the top. So one is like, are your embeddings efficient enough? Two is like, are you capturing all the data that you need? Three, are you using enough parameters? Four is the time. Five is like distributing across GPU clusters, and so on. So there's different areas around the generative AI training value chain, which Super can potentially have a lot of impact in. And some of the active research that we're doing, especially, is right at the start from the embedding side. And as we move down that chain, what we are trying to do is potentially come up with this number, like Mohammed had mentioned, like 20 to 30% of 20% to 30% of savings that we could get. So just for context, like what we are trying to prove is that Grok 3 cost $500 million to train across maybe millions of hours of GPU compute. So what we want to potentially prove and what we are doing active research on is, can we reduce that cost to maybe 350 million? And can we reduce the cost of compute to maybe like, if there was 1 million hours used, could we bring it down to 750,000 hours? So that is the work that Super can potentially enable and reduce the cost for any foundational LLM provider, Grok, ChatGPT, Anthropic, etc. So I hope that answers your question, Bank.
Good, very, very comprehensive, Krishna. Is there any other question, Charlie, or are we any from the audience? Oh, there's a question. Can you raise your hand again so we can pass you the?
I have a few questions. First, the platform you show is a chatbot, right? It's a classic chatbot?
No, it is not. It's a multi-agent system. It is 7 different AIs that have been trained for specific tasks. One AI's purpose is only to analyze the problem. One AI's purpose is only to generate code for D-Wave. One's purpose is only to, so these are specialized AIs.
And do you train it in a classic computer or in a?
Yes.
Okay.
Yes.
So do you have multiple AI agents? And they connect to quantum devices. Do you have your own quantum devices or you connect to another?
No, we don't build quantum chips. And part of the reason why we don't is because whoever builds a quantum chip will only recommend their technology. So D-Wave is never going to use IBM technology, or IBM is never going to use D-Wave technology because they are competitors, right? So we want to be hardware agnostic, and as a result of it, we don't have our own chip. We are going to have our own computers. So each kind of architectural computers we're going to have, but right now we don't have our own hardware. We use it from hardware vendors.
So it works all classic, right? Or where is the quantum in there?
When it gets submitted to quantum computers and gets solved on a quantum computer, and then the result is returned. And that is the only quantum part that you can get anywhere.
Okay.
Work with D-Wave directly, work with IBM directly. I mean, you're going to use a classical cloud to upload the data and everything. That's all classical. And that is never going to become quantum. So there is no such thing as quantum computers for word processing. It's not going to happen. Okay, so quantum computers are good at solving some things, and they are ridiculously bad at other things. Word processing, they are ridiculously bad at. You'll never use them for word processing. You would use them to securely communicate with a quantum computer. So there is a use case where you want to transmit your data to a quantum computer in a way that it cannot be decrypted. So you need quantum communication for that. So that yes. But other than that, these systems are always going to be classical. In fact, the systems that control the qubits, like when Krishna submitted the job, which variable went to which qubit, that system that does that on D-Wave side is a classical system. It's a classical control. Yeah. So the solver part only, the computation runs on quantum, but everything around it is classical.
Okay, thank you.
Does that answer your question, or are there other?
Yes, it
Yeah.
I
does.
think there were a couple of more questions that popped up on chat. How much resource power are you using to enable SuperQ to solve problems?
We have access to 5,000 qubits from D-Wave side, and tens of qubits on the gate-based machines. So gate-based machines have very few qubits compared to quantum annealers that have about 5,000 qubits, and that's what we have access to.
So
on the
just to-
GPU side, GPU clusters, and yeah, I mean that can scale up and down as needed.
And someone asked, will you ever own a D-Wave machine or IBM? That is a that is a deep question, which
Yes. We are already kind of in the process. I cannot say more about it, but yes,
yeah.
we will own our own hardware as well. But we will not build our own. We will not build a quantum chip. We are working in quantum sensing. So there is another aspect of R&D that we're doing, which is connecting quantum sensors to Super, and those will be our sensors. So we'll get into the hardware side when it comes to sensing, but not on quantum chip. Okay, our goal is that Super will leverage all the chips and get the best value out of them. Otherwise, we'll again get married to our chip, and we'll be recommending our chip to everyone. It defeats the purpose.
Yeah. Are you working with any academic institutions for ongoing researches? Yeah, I think right now, Samuel, I think we have quite a few universities, for example, like University of Lethbridge, University of Northern British Columbia in Canada, and there are a few more that I potentially can't say yet. I think it's conversations that are ongoing and should be announced soon. But there are a number of universities that we're working with across the Middle East, India, Canada, US, and we are working with them in different capacities. Some of them are essentially for super hubs, as well as some of them are to conduct specific topics of research. So there's different levels of collaborations across universities and research institutions. And the ones that I can potentially talk about right now are UNBC and University of Lethbridge. But there will be more coming out as we keep announcing them over the coming weeks.
We had a question in the audience as well at the back.
You guys talked about how it solves problems and optimizes processes and stuff, but not very clear on how it's going to be accessible to the public or when or.
So as of public access right now, we are onboarding the early access users that are coming in. And we have a wait list of around, I think, 300 or 400 people that are slowly getting access to the platform. By end of August, we want to open it for public views, where people can walk into the Super Hub at Economic Development Lethbridge, or there's another Super Hub in the Middle East that's coming up, where people can walk in and use the computer, can use Super, sorry. And there will also be Trailblazer access, where individuals can use it from the comfort of their home or wherever they're using it. And from there, I think public access will keep increasing as we start onboarding more users. But right now, there's a lot of beta testing and alpha testing going on as we add in users as we go on.
So you can access it in SuperHub here in Tech Connect. It's been operational since June, right? 18 June. So, and we have seen, I think, tens of and so actually you can access it now through the SuperHub. Through the web, it's going to come later in August, and then you'll be able to subscribe to it from home. Now, there are certain things that you would still want to do in the hub rather than from your home. We'll talk about that, and those are my last couple of slides actually that I want to talk about. So thank you, Krishna. So what I want to talk about, number one, is early access. So that question that you asked, how can you get web access? The fastest way of doing that would be to scan this QR code and fill out the contact form. Just say that you need early access and you were here in the Tech Connect Masterclass, and we will prioritize it. So in August, you'll be hearing back from us about details on how to access. So this is on the web access. Okay. Um, I'll also leave it on at the end. I'll leave this slide on at the end. So the other aspect is super hubs. What are super hubs? Think of them as quantum cyber cafes. Nothing like that exists anywhere in the world. The first one exists here in Tech Connect. Nowhere else in the world you can access a quantum computer from a terminal in a room, in any facility. Like I maybe in a lab in some high tech lab, maybe, but there is no publicly available resource like this anywhere in the world. The first one is here. Okay, the second one is going to be in Dubai, close to Dubai, 20 minutes away, in Sharjah, where there is a major economic zone, just like Economic Development Lethbridge. There is Sharjah Research and Technology Innovation Park. And then 20 such hubs are going to spin up around the world. Some of them in Canada, but they will all be coordinated from here, from Tech Connect. Okay, so it's a big deal. So I'm going to invite Renee at the end, to talk about the Lethbridge Super Hub. How can you access it? What are we doing here?
Yeah, we're so pretty excited about being the only one in the world, right? It's actually been pretty fun talking to people who have been working in this field. And back to the podium. All right, sorry, thank you. It's been pretty cool to go. Yeah, we have this first one in the world, and it's here and it's accessible, and it's like, what? Lethbridge? Why? Right? So we've been working for a long time in emerging technologies at Tech Connect. We started this incubator in 2012 with geospatial technologies. We've always had an opportunity for introducing blockchain. Was when we were educating entrepreneurs about what blockchain was and not about cryptocurrency, and that distinction and how that made a difference for smart contracts for their businesses. We also then started to do digital adoption around AI. So we were talking about AI 2 years ago when we were working with a company out of Finland to do AI assistance that would really help with our business advisors and help entrepreneurs understand that integration. So we've always been trying to be right at the forefront of this. So when Mohammed and Aaron came, who had been entrepreneurs in Tech Connect, and said, "We have this quantum. Would you be interested in being our first hub, because we really want to bring it here?" And I'm like, "Oh yeah, that's perfect, because we can now have access to our Southern Alberta companies that can actually create a competitive edge." And this is something that usually comes to a Calgary or an Edmonton because it's a bigger hub. But here's an opportunity for companies that are looking for that competitive edge, especially now when we're having to go out to new markets. We have supply chain issues. We have labor shortages, or having a hard time finding others for the workforce. These are all problems that we can help to solve with these larger data sets. So I really think that it's such an opportunity for us as a region to be lifted, but also then to be that model for the rest of the country and for out in the world of small places can do big things. And these are big ideas that we can actually bring to the table. And so I'm really going to encourage you that as a company or an organization or yourself, to really take a look at this technology. And you can come onto our website, the chooselethbridge.ca, look for our, what resources we provide. You find the quantum, and you can book a demo on there and just come in and play. Right? Because you've got a lot of information today. Imagine your brains are hurting. Mine was when I was trying to learn this. But come in and just see what it's like in front of you, and do and solve some problems just to get the feel of it, of what's like. We would have done the same thing with ChatGPT. When you first started learning it, you were treating it like it was a Google search until you actually figured out how it could optimize your work, right? And what that meant. So this is the same kind of learning curve to come in with your organizational problems. So whatever you've got that's a challenge right now, an issue right now, let's start to articulate what it is, and let's get it in there, and let's see how it could work, right? So this is all about experimenting. It's all about trying, but it's like, what could the possibilities be? And I think that's such a great place for innovators to work in what's possible, for companies to see how they can be optimizing, and how we can actually be much more competitive and serving up and being models for how this could be successful. So I really encourage you to be curious, to come in and just play with it and start to understand it so that you can see where some of the bigger problems that you might not even imagine that you could solve, like those wicked problems that we know that we so often can have in certain aspects of business, how it could be possible to solve those. So I hope you'll go online. I hope you'll book the demos and come in and be curious and just see the possibility. All right. So thank you everyone so much for coming out. Thank you, Mohammed, for great presentation. I could see some brains working overtime as they're trying to figure this out. It's definitely a learning curve. We do intend to create some more sessions here. So we will be following up with you with some questions. If you're in a particular sector, like in manufacturing, agri-food, agriculture, we'll be asking whether you'd like to go dig deeper into seeing some use cases that are specific to that, and then just doing a deeper dive into just rather than just the introduction to this. So you can expect to hear more from us. So thank you very much for coming out. Hope you'll linger. If you have some other questions, come on up and let's talk. But I just really appreciate your time today, and have a good day.